So we have to differentiate sine inverse of x to the power 5. Differentiating sine inverse is 1 over the square root of 1 minus whatever's in the brackets squared. We then have to times this by the brackets differentiated. X to the power of 5 differentiated is 5x to the power of 4. So this is multiplied by 5x to the power of 4. We could then multiply this by the 1 on the numerator and have a numerator of 5x to the power of 4. Then on the bottom, the x to the 5 all squared is x to the 10. So this will be the square root of 1 minus x to the power of 10. X cubed plus y to the 4 is equal to 12. We differentiate each term in turn. Differentiating x cubed gives 3x squared. Now differentiating y to the 4, differentiating with respect to y gives 4y cubed. But we have to multiply this by dy by dx, y differentiated. Differentiating 12 gives 0, so this is equal to 0. To find dy by dx, we now need to rearrange this. The 3x squared, if we subtract that from both sides, that gives us 4y cubed times dy by dx, and on the right hand side we'll then have negative 3x squared. And to find dy by dx, we now divide the negative 3x squared by the 4y cubed. Negative 3x squared over 4y cubed. You could write the negative sign at the front and write this as negative of 3x squared over 4y cubed. Dy by dx is given by y dot over x dot. Now x dot is equal to dx by dt. Differentiating 2t cubed plus 4t with respect to t gives us 6t squared plus 4. Then y dot is dy by dt. Differentiating y with respect to t will be 12t cubed. Dy by dx is then y dot over x dot, which is 12t cubed over 6t squared plus 4. To do this integral, we need to first of all take the expression inside the integral and express it in partial fractions. So we let 2x plus 3 over x times x plus 3 equal a over x plus b over x plus 3. We then multiply through by this denominator x times x plus 3. We multiply each term in turn. Multiplying 2x plus 3 over x times x plus 3 by this, the x times x plus 3 cancels and we're just left with 2x plus 3. So this is equal to multiplying a over x by x times x plus 3, the x's cancel, and you're just left with a bracket x plus 3. Finally multiplying the b over x plus 3 by x times x plus 3, this time the x plus 3's cancel, and you're just left with b times x. What we're going to do now is fit in some values for x so that we can find the values of a and b. We'll call this equation 1. Fitting in first of all x equals 0 will make this last term 0, and this will be 0 plus this will be 3a, and 0 on the left hand side will give this to be 3. So by fitting in x equals 0 into this equation, we get that 3 is equal to 3a, so that a must be 1. Now if we fit in the value x is minus 3, this term will disappear. The left hand side will become 2 times minus 3 plus 3 is negative 3. This will be 0, and this will be negative 3 times b. So fitting in x is negative 3 gives it negative 3 is negative 3b, which means that b is also equal to 1. So our partial fractions are 2x plus 3 over x times x plus 3 is a over x, 1 over x, plus b over x plus 3, also 1 over x plus 3. Our integration will now become, instead of the integral of 2x plus 3 over x times x plus 3, we replace this by the two partial fractions. So it's the integral of 1 over x plus 1 over x plus 3 dx. Integrating 1 over x gives us log mod x. Integrating 1 over x plus 3 gives us log mod x plus 3, plus our constant of integration c. We can combine these first two using the first law of logs. This will become the log of the mod of x bracket x plus 3, plus our constant c of integration. First of all, we'll call this integral I, so that we have to work out I between 0 and pi. Integration by parts, or definting. We draw a definting table. Split it into 4 quadrants. The part of the integral that we want to differentiate is the 2x. The part that we want to integrate is the sin x. Differentiating 2x is 2. Integrating the sin x is minus cos x. And then the integration by parts formula, using this definting table, to work out I, we work out 2 times 4 minus the integral of 3 times 4. 2 times 4 is 2x times minus cos x, which is minus 2x cos x, minus the integral of 3 times 4, which is 2 times minus cos x, or minus 2 cos x. Because we've got a minus outside the integration and a minus inside, we can just make this a plus. The integral part of the answer is minus 2x cos x. We still need to integrate the 2 cos x, but that just gives 2 sin x. So I is equal to minus 2x cos x plus 2 sin x. We forget about the plus c here because we are going to be fitting in the two values 0 and pi. So the original integral from 0 to pi of 2x sin x dx is equal to I evaluated between 0 and pi, where I is the minus 2x cos x plus 2 sin x. We then fit x equals pi into the first set of brackets and x equals 0 into the second set of brackets, and we subtract the two answers. Fitting in x equals pi is minus 2 times pi times cos pi plus 2 sin pi. Into the second bracket, separated by a minus, we've got minus 2 times 0 times cos 0 plus 2 times sin 0. Cos of pi is negative 1. Sin of pi is 0. Cos of 0 is 1. Sin of 0 is 0. 2 sin pi, well, that will just be 0. So also will minus 2 times 0 times cos 0. That will be 0. And 2 sin 0 will also be 0. So this is the only part of the answer which will contribute. Minus 2 pi times the cos of pi, which is minus 1, is minus 2 pi times minus 1, which will give us plus 2 pi. So So that plus 2 pi is the answer to this integration. We do this differential equation by separating the variables. The y is on the left hand side and the x is on the right hand side. So dy by dx is equal to 3x squared y. Take the dx across and multiply. So that dy is equal to 3x squared y times dx. We can then take the y over and divide by it. So we've got dy over y on the left hand side, and on the right hand side we're left with 3x squared dx. We've now separated the variables, so we integrate each side of this equation. So the integral of dy over y is equal to the integral of 3x squared dx. The integral of dy over y is log y. The integral of 3x squared dx is x cubed plus c. If we now take e to the power of each of these on the left hand side and on the right hand side, e to the log y is equal to e to the x cubed plus c. The reason we're doing this is because e to the log y will give us y. So y is equal to, now e to the x cubed plus c, we can separate this using the laws of indices to become e to the x cubed times e to the c. If we now replace the e to the c, which is just a constant, by a, we get the general solution is that y is equal to e to the x cubed times a, or ae to the x cubed. First of all, asked to work out uv in Cartesian form. So we multiply 2 plus 3i times 4 minus I, and we put each of them in brackets. We then multiply out these brackets. 2 times 4 is 8. 2 times minus I is minus 2i. 3i times 4 is plus 12i. And then finally, plus 3i times minus I is minus 3i squared. Minus 3i squared, I squared is minus 1, so the minus 3i squared will become plus 3 at the end. The minus 2i plus the 12i gives us plus 10i. So we've got 8 plus 10i with a plus 3 at the end. The 8 plus the 3 gives us 11. So this is equal to 11 plus 10i. We're then asked to plot uv, which is 11 plus 10i, on an argand diagram. So we draw our real axis, our imaginary axis, 11 on the real axis, 10 on the imaginary axis, and where they meet, we plot our point 11 plus 10i. We're asked to find the modulus and argument of z. Root 3 minus I. First thing we'll do is we'll plot root 3 minus I on an argand diagram. So we plot the point root 3 minus 1. Drawing our real and imaginary axis. Root 3 in the real axis, minus 1 in the imaginary axis. We then draw this triangle, and I'll enlarge this. To find the modulus or mod z is given by the square root of the sum of the squares of the x and the y coordinates. So mod z is equal to the square root of root 3 square plus minus 1 square. Root 3 squared is 3, minus 1 squared is plus 1, square root of 3 plus 1, square root of 4 is 2, so mod z is equal to 2. To find the argument of z, first thing we do is, in this small triangle here, we find the size of this angle. Say we call it x. Then the tan of x will be equal to 1 over root 3. That's an exact value. The angle whose tan is 1 over root 3 is 30 degrees, or in radians pi by 6. Now we want to find the angle corresponding to this in the fourth quadrant. The other angles corresponding to pi by 6, first quadrant angle is pi by 6, second quadrant angle is 5 pi by 6, and then in the third and the fourth quadrants it's the negatives of each of these. So third quadrant negative 5 pi by 6, fourth quadrant negative pi by 6. We want the answer that's in the fourth quadrant, so the argument is negative pi by 6. Arg z is negative pi by 6. So, the answers to the questions. Find the modulus and argument of z. Mod z is 2. Arg z is negative pi by 6. We're then asked to write z in polar form. So in polar form, z will be equal to 2 outside the brackets, and then cos of the argument, negative pi by 6, plus I sine negative pi by 6. So we've got an arithmetic sequence, 4, 16, 28 and so on. First thing we'll do is we'll write down the first term, which we call a, so a is equal to 4. The common difference, we're adding on 12 each time, so the common difference d is 12. First thing we're asked for is the 20th term in the sequence. The nth term of an arithmetic sequence is a plus n minus 1 times d. So the 20th term will be a plus 19d. So that's equal to 4 plus 19 times 12, which is 232. So the 20th term of this sequence is 232. For part B, we're asked to find the sum of the first 20 terms. Now the formula for the sum to n terms of an arithmetic sequence is n over 2 bracket 2a plus n minus 1 times d. N will be equal to 20. So n over 2 outside the brackets will be 10. So we're asked for s of 20. S of 20 will be 20 over 2, which is 10, times 2 times 4, plus n minus 1, which is again 19 times d, which is 12. And this works out to be 2,360. So the sum of the first 20 terms of this arithmetic sequence is 2,360. This time we have a geometric sequence. First term a is 4. Common ratio, to work out the common ratio we can divide the second term by the first. So the common ratio would be 12 divided by 4, r is equal to 3. We want to find the 8th term of the sequence. The nth term of a geometric sequence is ar to the n minus 1. So the 8th term will be ar to the 7. So that is 4 times 3 to the power 7, which is 8,748. So the 8th term of this sequence is 8,748. Part B, we're asked to work out the sum of the first 12 terms. Sum to n terms of a geometric sequence is given by the formula a bracket 1 minus r to the n over 1 minus r. N is equal to 12, a is 4, and r is 3. So S12 will be equal to 4 bracket 1 minus 3 to the power of 12 divided by 1 minus 3. And this works out to be 1,062,880. And that will be the sum of the first 12 terms of this geometric sequence. All we need to do here is to find if there's particular values of A, B, C and D for which this conjecture doesn't work. If it doesn't work for one particular set of values, then that means that it's not true. So say we choose A is equal to 2 and B is equal to -4. C equal to 1 and D is equal to -3. So that A is greater than B and C is greater than D. But when we work out AC, AC is equal to 2 times 1, which is 2. BD is -4 times -3, which gives us +12. And we notice that for these particular values, AC is actually less than BD. So AC is not greater than BD for these particular values of A, B, C and D. And this shows that the conjecture is not true. We're asked to prove by contradiction that if n squared is odd, then n is also odd. So we start by assuming that if n squared is odd, then n is even. That means that there must be an even number, n, such that n squared turns out to be odd. Now if n is an even number, then n is equal to 2 times some number k, where k is a natural number. Which means that n squared will be 2k all squared, which is 4k squared. 4k squared can be written as 2 times 2k squared. So n squared is equal to 2 times 2k squared. Now if n squared is equal to 2 times 2k squared, if k is a natural number, 2k squared is also a natural number. So n squared is 2 times another number. Now if n squared is 2 times another number, that's the definition of n squared being an even number. So we know that n squared must be even because 2k squared is an element of the natural numbers. This contradicts what we assumed at the top here. So the assumption that we made is contradicted. So we've proved by contradiction that if n squared is odd, then n is also odd.